Hey guys, it's Alpha with the Adaptive Immune System video. Sorry I couldn't make it to class, but happy to still be able to participate. So we have our immune response timeline, and that's when you have an infection. And it starts with the innate immunity, and then it becomes the adaptive immunity. And we're focusing in on these guys here, B lymphocytes and T lymphocytes. They don't start working until about a day after infection. Alrighty, so we see here we have our multipotential hematopoietic stem cell. And then it differentiates into all the different blood cells, and we are looking at the T lymphocytes and the B lymphocytes, and we'll talk a little bit about the plasma cell. Now to look at primary and secondary lymphoid organs. Our primary organs are thymus and bone marrow, and that is where the T and B cells develop from our hematopoietic stem cell. Now the thymus, T for T cell, and then bone marrow, B for B cell, and that's where those cells originate. Then the secondary lymphoid organs are the sites of action. That's where the T cells and the B cells do work. And they weighted these different organs, and whenever a pathogen presents itself, that's when they kick into action. We'll talk about that a little bit later. So the bone marrow produces the hematopoietic precursors, and from there they could go and stay in the bone marrow, or they could go to the thymus. If they stay in the bone marrow, they differentiate into B cells, and when they go to the thymus, they differentiate into T cells. And we have two types of T cells, CD8, which is our killer T cell, and our CD4, which is our helper T cell. And we'll talk a little bit about those functions later as well. When the hematopoietic precursor gets into the thymus, it becomes a lymphoid progenitor, and this DN stands for double negative thymocytes. And it means that they don't have the T cell expression, and as they differentiate, they end up getting the T cell receptor, and they're expressing it. And if there's neglect, because we'll talk a little bit more about the reasons why we have the neglect, it's usually because of autoimmune recognition, those T cells will then go on and die. And then from there, we have a committed CD8, CD4, and they will differentiate into our mature T cells. So once again, our primary organs are the sites of development. Here we have our thymus, we have our bone marrow. The thymus, T makes the T cell, bone marrow makes the B cell. They go into capillaries, and then they go off to our secondary organ, the spleen, the lymph nodes. That's where they do all their work. The highly antigen-specific adaptive lymphocytes hang out and wait in these secondary tissues for antigens to present themselves. Now, they don't get there on their own. They're either sent by other innate cells or carried directly to the secondary tissues by innate cells such as the dendritic cell. So we got T cells and B cells waiting at secondary lymphoid tissues. Now what? Good question. Alrighty, so we have a single progenitor cell that's going to give rise to a whole bunch of different T or B cells. And that's because of polymorphism, polygeny, and recombination. The polymorphism, there are multiple alleles for the same gene, and then the polygeny means that there are multiple genes at separate loci that encode for isotypes of the same gene. And then because of recombination, there's going to be swapping of parts of genes during cell replication. So we put all these together and we have a lot of variability. Then we end up removing the potentially self-destructive immature lymphocytes by clonal deletion. And that was what I was alluding to before. Whenever the antigen that these lymphocytes recognize happen to be your own tissues, that's a bad thing. We can't have our lymphocytes attacking our own tissues, so they are killed. And so then we have a pool of mature, naive lymphocytes that haven't yet been introduced to an antigen. And when an antigen comes in, it's not going to be recognized by all of them because of all of this variability. But the one that does recognize that antigen is going to then go through cloning and replicate itself over and over and over. And then they're going to send all of these clones out to attack circa Star Wars. Alrighty, clonal expansion leads to memory. Here we have our naive lymphocytes, in this case it's a B cell, and here we have our memory B cell. Now this naive B cells, they haven't yet seen any antigens. And here we have our anti-X B cell, our anti-Y, purple is X, green is Y. When the purple anti-X B cells are introduced to an antigen, they mount the primary anti-X immune response, and they shut that down. Once that pathogen is eliminated, some of those B cells linger back in the secondary tissue as memory B cells. But here we still see that anti-Y is still naive because anti-Y has yet to see its antigen. So now in our secondary tissues, we have our memory B cells and we have our naive B cells. the memory is B, or the memory is anti-X, the naive is anti-Y. Now we have a pathogen that presents antigen X and antigen Y, and it's going to mount a secondary anti-X response, which is much steeper and with a much greater amplitude because these memory cells have already seen it and they more efficiently do their job. But the naive B cells that recognize the antigen Y have yet to see antigen Y. So when they first are introduced to antigen Y, they mount a primary anti-Y response, just like the primary anti-X when X was still naive. This right here is the foundation of vaccination, that by providing a little bit of this antigen, we mature these B cells away from naive to memory, where they're able to mount a response, an immune response, to a greater amplitude and a faster degree. Alright, here's adaptive response for TMB, and it's a Venn diagram. I'm not going to go ahead and read it to you guys, but I'll describe it on the next slide. Feel free to come back and check it out if you have free time. So B cells, they have B cell receptors that recognize antigens, and then they shoot out antibodies that go and then bind to the antigen if it's on the pathogen, and it signals downstream for other elements that we'll talk about in a little bit. The thing that's pretty cool about these B cells and their antigen recognition is that they can recognize tons of things from viruses, bacteria, to DNA, proteins, peptides, and even metal. T cells, on the other hand, are only able to recognize peptides that are present in a MHC complex, and the peptide must be presented by an antigen-presenting cell like a dendritic cell. So when B cells have an antigen, they develop into a plasma cell that then secretes antibodies for that antigen, and those antibodies then go and bind to the pathogen with that antigen. Now, those antibodies have three main functions. They neutralize the pathogen and prevent it from migrating into and out of cells. They ospinize the pathogen, which means they facilitate phagocytosis by coating the surface with the antibodies that then phagocytic white blood cells are able to recognize, and then they eat it all up. And then they have complement activation. We haven't yet learned about it. Actually, I didn't go to lecture this morning. We may have. But complement activation is very similar to the ospinization, except for that instead of the antibodies being recognized by the macrophages, now it's this complement protein that these macrophages or phagocytic immune cells recognize, and then they opsonize the pathogen in a similar fashion. Alrighty, we have our CD8 T cell. It's the killer T cell. We haven't yet learned the details of exactly how it goes through and kills the pathogen, but it's written out over here. It comes down to secreting this enzyme perforin and granzyme, and then it makes that cell cytotoxic, and the pathogen dies. The CD4 T cell, or the helper T cell, doesn't kill the pathogen. It secretes interferon gamma to activate macrophages, or it makes IL-4, and that activates B cells. So our innate immune response, our initial response, kind of causes the infection and the pathogens to plateau. And then our adaptive immune response causes the pathogens and the infection to disappear. And that shows our virus titer going down because of the adaptive immune response. So what happens if there's a dysfunction? If there's a dysfunction in our innate immune response, we never see that plateau. We don't get the adaptive cells activated. So the virus just continues to grow. Now, if we have a dysfunction of our adaptive immunity, we'll see our virus titer plateau, but then there's no adaptive response and it grows. Adaptive immunity recognizes specific antigens, there's activation, proliferation, and there's memory, and it's responsible for killing the virus off. These are my works cited. Sorry, it took a little while. There's a lot of stuff in the adaptive immune system, and I wasn't quite sure which parts were the most important, so I put in as much as I could, as quickly as I could. Have a good rest of PBL. See you guys.